Okay, so pause the video and read the question. Hopefully you've done that. We want to find the frequency of the sound that's required to get a good scan to have a 1 millimeter wavelength. So we're going to use V equals lambda F. V is our wave speed, how quickly the wave can travel. Lambda is the wavelength, the distance from one crest to the next. Frequency is the time it takes, or how many cycles we get per second. So how many waves per second we have measured in hertz. So we're told that V is 1500 meters per second. That's the speed at which waves travel through body tissue. And we're told that we're going to be in SI units here. Our wavelength is 0.001 meters. So I had to convert from millimeters to meters. So it's just F is V over lambda. We get 1.5 times 10 to the 6th hertz. Would be, according to this problem, the ideal frequency to use. Okay, we'll see. We get a different answer in a minute, which is kind of weird. All right, here's a different problem. So pause the video and read this question. Okay, hopefully you've done that. Part A, we want to find the wavelengths of audible sounds from smallest frequency to largest frequency. We're going to use V equals lambda F again. We'll use, this is a good global kind of value. V is 344 meters per second for the speed of sound in air. For the 20 hertz frequency, we just plug and chug here. Lambda will be V divided by F. We get 17 meters. So the smallest frequency sounds that you can hear are 17 meters long. Giant, long sounds. What we call ultrasonic frequencies are even longer than that. And we can't hear them because they're less than 20 hertz. Our highest frequency we can hear is about 20,000 hertz. And again, just using lambda as V over F, we get about almost 2 centimeters. Notice, by the way, lambda and F are inversely proportional. Big frequency means small wavelength. Small frequency means big wavelength. Okay, part B, we're going to play the same game, this time with light. 400 to 700 nanometers are about what we can see. That's the range of visible light. Remember, light is just a wave. And the speed of light in a vacuum, we're probably actually in air here. Yeah, that's where we do most of our seeing, is in air. So we really should be using the speed of light in air. It's a little bit smaller than this, but this is good enough for the purposes of the problem. So for the 400 nanometer wavelength, here they gave us the wavelength. We want to find the frequency. A nanometer is 10 to the negative 9th meters. So we get a frequency of 7.5 times 10 to the 14 hertz. And for the 700 nanometer, 4.3 times 10 to the 14th hertz. Again, we're still just using V equals lambda F here and solving for F. Part C is a different question. This comes from the same book. It's a different question about ultrasounds. And again, like in this problem, they said ultrasounds use frequencies higher than 20,000 hertz. So we've got 23,000 hertz is our frequency we'll be using. We want to know what's the wavelength that we'll have if those waves were in air. So for part 3, here's our frequency, V equals lambda F again. We get about 1.5 centimeters for our wavelength. Part D says, now play that same game, but now do it in the human body. So we're using 1480 meters per second as the speed of sound through human tissue. And we get about 6 centimeters as our wavelength. So this is weird because in this first problem, they told us, this is from the same book, that to get a detailed image, they need the wavelength to be about on the order of a millimeter. And then here they're saying, nah, that's okay, we can be 60 times larger than that and be 6 centimeters. So I think this problem is more trustworthy for what actually happens in ultrasounds rather than this one.